Let's do a problem related to bacteria. The doubling period of a bacteria population is 15 minutes. At time t equals 120 minutes, the bacteria population was 80,000. What was the initial population at time t equals 0? So before we get started, it's useful to know that we can model this growth with an exponential function. P of t equals a times b to the t. Let's take a look at what information we're given. So we're told that the doubling period of the bacteria population is 15 minutes. That means it takes 15 minutes for the bacteria number to double. So after 15 minutes, however much you start with, the amount doubles. It also tells us that at time t equals 120 minutes, the bacteria population was 80,000. So we know that when t equals 120, there are 80,000 bacteria. We also know that the amount of time it's going to take for these bacteria to double is 15 minutes. In other words, 15 minutes after 120 minutes, so in 15 more minutes, so at t equals 135, that's 15 plus 120, the bacteria population is going to be double what it was before. So it's going to be like 2 times 80,000 or 160,000. It's useful to know these two things. So it's useful to know that P of t is 80,000 when t equals 120. And that P of t is equal to 160,000 when t equals 135 minutes. Because if we know these two things, we can actually plug them into our equation here and solve for a and b. In particular, we're being asked what was the initial population at time t equals 0. We know that when we plug 0 into this equation, we get a out, and that is the initial population. So we know a in this equation is the initial population. So if we can use this information to solve for a and b in that equation, we'll know what a is. In other words, we'll know what the initial population is. So the question is, how do we use this information to solve for a and b? How do we do that? Here's what we can do. We can take the first equation and we can plug in for t 120, and we can plug in for P of t 80,000. So I can put 80,000 equals a times b to the 120. And then I can do the same thing for this one right here. I can put 160,000 equals a times b to the 135. At this point, we have two equations in two unknowns. So we have an equation here with an a and a b in it, and we have an equation here with an a and a b in it. And when you have two equations and two unknowns, you can take this strategy to solve for the unknowns. What's the strategy? We solve for one of these unknowns in one of the equations. So what I mean by that is we could take the second equation and solve for one of the variables. Maybe we solve for a. So I can solve for a here, and then I can plug that into the a on the left in the other equation. And what's going to happen is the second equation will turn into an equation that just has b in it. So I'll show you what I mean. So I take this equation, and I'm going to solve for a. So a is going to be equal to 160,000 divided by b to the 135. That's if I divide both sides by b to the 135. So I go divided by b to the 135. Okay, now I can take this number here and I can plug it in for the a on the left. So if I do that, I get 80,000 equals 160,000 over b to the 135 times b to the 120. So I've taken this and plugged it into the a spot in my second equation. Look at what happens if I simplify this. So let's see here. We know that 80,000 is half of 160. So if I divide both sides by 80,000, in other words, if I go, okay, divided by 80,000 and divided by 80,000, on the left, we just get 1, and on the right, we cancel and get a 2. So this will simplify into 1 equals 2 times b to the 120 over b to the 135. And then I can cancel some of these b's right here to get 1 is equal to 2 over b to the 15. At this point, if we cross multiply, we'll get 1 times b to the 15 equals 2, or b to the 15 is equal to 2. Now, if I raise both sides of this to the 1 over 15, or take the 15th root, I will have solved for b. So b is equal to 2 to the 1 over 15, or the 15th root of 2. Okay, it's really handy to know that this is b. So it's useful to know that this is b, because we can come back up here and look at this equation right here. So take a look at this one. We have a in terms of b. So let's bring that down. A in terms of b is 160,000 over b to the 135. So if I stick my b into this equation, so if I put my b into that equation here, in other words, if I stick 2 to the 1 over 15 in there, and then simplify and type this into a calculator, we're going to find that a is equal to 625 over 2, or 312.5. So now we know what a is and we know what b is. In other words, we have an equation for p of t. So p of t, remember, is a times b to the t. And we know that a is 312.5 and that b is 2 to the 1 over 15. So here's an equation for the growth of this bacteria. If I want, I can distribute the t value, so let's do that. Okay, so this equation models the bacteria growth. Now, what were we asked in the beginning? We were asked to find what the initial amount of bacteria there was. So we were asked to find the initial population of bacteria. So our question was, P of t equals what when t equals 0, when we start at time t equals 0. So we can figure this out by plugging 0 into our equation. To the 0 is just 1, so we get 312.5. Or you can just remember that the value right here, or your A value, is always the initial amount. So remember, this is always your initial amount. So we start with 312.5 bacteria, which is the answer to part A. Okay, let's look at a part B. Find the size of the bacteria after 4 hours. Now this part's going to be a little shorter because we already have found our equation. We know P of t equals A times B to the, well, let's actually just write down the equation we already came up with. So we know that P of t is equal to 312.5 times 2 to the t over 15. So we have that from earlier. We want to find the size of the bacteria after 4 hours. So what is P? P of t equals what after 4 hours. Now, it's really important that we remember that in this equation we just found, T here is in minutes. So this T is in mins. We want to know the size of the bacteria after 4 hours. So since this unit's in hours, we cannot just plug the 4 into the T value. We need this 4 hours to be in minutes instead. So before plugging in a T, we have to convert 4 hours to minutes. So 4 hours is actually equal to 4 times 60 minutes because there are 60 minutes in 1 hour. So this is equal to 240 minutes. So after 240 minutes, we're going to have P of 240 equals 312.5 times 2 to the 240 over 15. Or 20,480,000 bacteria. So quite